Welcome to Fun with Science, Engineering, and Technology. My name is Mr. Ross, and today we're going to discuss Sir Isaac Newton and some of the gravity theories that he came up with. And our Newtonian physicists this morning are Kara and Caroline. So, what do you know about Sir Isaac?
I know he was born.
Okay, you can read this one and we tell them a little bit about Sir Isaac.
Sir Isaac Newton was born in 4th January 1643 and he died on the 31st of March 1727. He published a work in 1687 that included his ideas about gravitational force, and he made revolutionary advances in mathematics, optics, physics, and astronomy.
Yeah, one of the stories about Sir Isaac is that he was sitting underneath the apple tree and the apple fell down and hit him on the head. You remember that story? You heard that one before?
Yeah.
And he all of a sudden came up with the idea of gravity. Well, that's probably really not a true story. Right? I'm pretty sure that he may have gotten hit on the head by an apple, but that isn't what gave him the idea. But probably come a little closer to the idea of what caused him to come up with all these theories about gravity was maybe an apple did fall out of the tree, right? And it fell from the lower branch, went down to the center of the earth, or fell towards the center of the earth, and also went up on the top of the tree. When it fell, where did it go? Same place, right? Down onto the ground towards the center of the earth. So Sir Isaac probably looked at that and said, okay, well, up there's the moon, right? It's just like a big old apple, a little higher up in the tree. Why doesn't it fall down towards the center of the earth? And that got him to thinking about gravity, right? And really what he did is he published a document, right, on gravity, his theory on gravity, but it didn't have anything to do with apples, right? What it had to do was with all the planets and so forth, right? And what kept the moon up circling around the earth, we know you're the earth, we got this moon out here, right, and it's revolving around the earth, but why doesn't it fall down and hit the earth? Why didn't it just like the apple? Why didn't it fall down? So that's what he actually wrote the paper about. So what we're going to do is first of all let's talk a little bit about gravity.
Okay.
Right? We have a book. What's it doing?
It's laying flat on the table.
It's not doing anything, is it? It's just sort of laying there.
Yep.
Is there anything acting upon that book?
Nope.
No? Nothing? You sure?
It's just laying on the table.
Yes, so.
It's just laying there.
Yeah.
Nothing's happening to it. All right, so, but really, what's happening is gravity's pulling down on the book, right? If we were to take it and put it on the scale and weigh it, it would have some weight,
Yeah.
right? Just like we put you on the scale and weigh you, you have some weight, right? And why do you have that weight?
Gravity?
Because the gravity is pulling it down on you, right? And that's the force of gravity pulling down on you is what the weight is, right? So that book has some gravity pulling down on it. Why isn't it falling like the apple out of the tree?
Because it's laying flat on the surface.
It's laying flat on the surface, that's right. Right, but why did the whole thing just fall down? Well, let me all right. Gravity's pulling down on the book. The weight of the book is pushing down. It's pushing down against the table. And the table is pushing back up with the same force. So the two forces are equal. The force of the weight of the book down and the force of the table pushing it up, and they're equal, and therefore the book is standing still. Right? If they weren't equal, if that book was really, really, really heavy and the table wasn't able to push up with enough force, what's going to happen? It's going to collapse the table and the whole thing will fall down. So now, what's the book doing now?
Pushing down on your hand.
It's pushing down on my hand, right, with the weight of the book, and what's my hand doing?
Pushing it back up.
Pushing back up. And so nothing's happening, right? What if I do that?
It falls.
It fell, right? Okay. So, but it started out, what? It started out at 0 speed, right? And as it fell, and we couldn't really see it, but as it fell, it started going faster and faster and faster.
Yeah.
Right? And on Earth, the force of gravity pulling down on this book, right, causes us to start out from 0, get going faster and faster, and what it does is at 32 feet per second squared. For every second that it falls, it gains speed 32 feet per second, just like miles per hour. Right. On paper, right? Now, have you done this one before?
No.
You haven't done this one before? I'm going to drop the book again, so don't jump.
Alright.
So what if I take these two, right? I'm holding them, right? This hand is holding the book up with the force of the weight of the book, right? And this paper weighs something, and this hand over here is not working near as hard as holding the piece of paper. What happens if I drop both of them now? What's going to happen?
The book goes faster.
The book's going to go faster, you think?
Yeah.
All right, you were right. The book hit the table faster, but both things had the same force of gravity on them, right? And the reason this paper didn't drop as fast is because this comes down through the air, right? And the air is pushing up and makes it float. If this were a piece of feather or a little piece of cotton or something, I dropped it, it would go even slower, right? What if I take the piece of paper? Now, if I've done anything to this piece of paper except rumple it up, it still weighs the same, right?
Yes.
Right? Now then, if I drop the two of them, which gonna hit the table first?
The paper,
The paper?
I'm guessing.
You sure?
Even.
They were even, right?
Yeah.
They were even, so they both dropped at the same speed, right? And the reason was is because, of course, there's air pressure pushing up against this book as it falls, but the book is so heavy, right? This doesn't have any. Where this little piece of paper, right? So if we were to we go out into outer space, someplace where there was no atmosphere, we go to, I don't know where that is. Well, let's go to the moon. Okay, the moon does have a little tiny atmosphere, but it's not anything like ours, right? And we were to take these two like this, and I were to drop them, guess what would happen?
The paper will go faster.
Oh, no, they would go at the same speed, right? They would drop down at the same speed. Right, and they both hit the ground at the same time. Even though,
The paper's light.
and if I were to take a feather, and I go to the moon, where there's no air, no atmosphere, and I drop the book and I drop the feather,
Same.
they're going to fall at the same rate. They're going to be accelerated at the same rate. If we take all the air off of the Earth, right, and we drop them, they're going to both accelerate, right, start falling. They start out at 0, get faster and faster as they fall, and at 32 feet per second squared is the rate they're going to be accelerated as they go. So Sir Isaac, Galileo did an experiment off of the Leaning Tower of Pisa. You know where the Leaning Tower of Pisa is, right? It's in Italy. It's one of those pizza towers. and it leans, all right? They build it straight up, but over the period of years, it sort of leans over. So you could go out to the edge of it and drop something straight down, and it wouldn't hit the side of the building, right, and fall down. And he did, back in the hundreds of years ago, he did a little experiment, just basically what we did, like this. He took a couple objects, right, different sizes, different weights, right, and dropped them off the Leaning Tower of Pisa, and timed how long it took them to hit the ground. And they both hit the ground at the same time. So he proved the same theory. We don't have a Leaning Tower of Pisa, so we have to do it here. All right? So, now, where do we go next from this? Right? So, can you see when I drop this down, can you see it starting at 0 and get faster and faster as it goes?
No, it just falls.
It just falls. I mean, if we were to do it in slow motion, we could probably see it, speed up as it goes. So let's do a little experiment just to show that things do accelerate as we put a force to them. I have a little car. Okay. It's one of my favorite little cars. Piece of string. What's this thing?
I love her.
That's a pulley, right? And I have my favorite plastic bag and a little piece of weight on it, right? Right, so what's happening with my plastic bag with little piece of clay in there. If I let go of it, what happens?
It goes down.
It goes down. Why does it go down?
Because the piece of clay is pushing it down.
Because a piece of clay is pushing it down.
The weight.
The weight, and what causes the weight?
Gravity.
Gravity, right? So gravity is causing the weight, a force, which is going to push us down. So what we can do, if we take, Caroline, you hold the pulley over there for a minute, right? Right over here. You got to hold it by this little
All right.
little thing, right? And hold it down, 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 down. There, like that. So now, if I take and we let that start falling, what do you think's going to happen to my little car?
It's
gonna
gonna
start-
start rolling.
It's going to start rolling, right? Is it going to go the same speed all the way across?
No.
No. Why?
Because as that goes down, it gets more heavy and picks up speed.
It doesn't get any heavier, right? But it's going to pick up speed because the gravity is accelerating it, right? So let's hold this straight up and down like this, right? And I'm going to let go of the string and let's see what happens. So what happened?
It picked up speed.
Hmm?
It picked up
the
speed.
speed.
It picked up speed. Even though it went over this little hump, it would have been nice if we had a real flat surface, but it picked up speed. Okay? Now, what else is happening? Right? If, watch that weight, what happens to it when it gets a... It hit the ground, didn't it?
Yeah.
Right, now, watch when it hits the ground and tell me what happens to the car.
Keeps
Car
going.
stops when it hits the ground.
No, it
The
keeps
car stopped when it hit the ground?
No.
No, it kept on going, right? And that was one of the other things that Newton came up with. This guy Newton just messed up our whole lives. Right? He says that your bodies, right, like that car, tend to stay at rest, right? Not move, like I do in the morning. I want to stay at rest, right? And once they do get moving, they tend to stay moving. Right? And they'll move in a straight line, right? Once you get it moving, right? And if I were to take this book, right, somewhere and I throw it, right, and get it going, it's going to continue to go at that same speed, unless something acts upon it, right? In our particular case where we're standing in here, if I throw this book, it's eventually going to slow down, right? Because one of the things that's going to happen is the air friction coming across here is going to slow it. The other thing that's going to happen was if I throw it across the room, what's going to happen?
It's gonna hit something and fall.
Well, it's going to hit something, right? If I don't throw it very hard, what's it going to hit?
Nothing. It's just gonna.
If I don't throw it very hard, it's going to go down and hit the floor. Why does it hit the floor?
Gravity.
Gravity, right? Because if I'm pushing it, I'm throwing it this way, all right, and I get it going some speed, and gravity is pulling down on it and causing acceleration, make it fall down. And if I throw it real fast now, in here, instead of hitting the floor, what's it going to hit?
The wall.
A wall. Why?
Because your force beats the gravity.
Well, no, gravity's still there. It's going to still, pull it down and make it hit on the floor. But if I throw it real fast, gravity doesn't have enough time to pull it all the way to the floor before it hits the wall. If we open the window and I throw it real fast out the window, what's going to happen?
It'll fall to the ground.
It's going to fall to the ground, right? And if I were to throw it really, 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 really fast,
I'll go a little farther, but it'll fall down.
it'll eventually fall to the ground. Okay. So, what is this thing called gravity? Some sort of a force, right?
Yeah.
All right, Caroline, can you read this one? Tell us what the law of universal gravitation is.
Alright, it is every object in the universe attracts every other object with a force directed along the line of centers for the two objects that is proportional to the product of the masses and inversely proportional to the square of the separation between the two objects.
Very good. A lot of words in there, right?
Yeah.
You know what they all mean? Huh?
I don't know.
Okay, it says it's proportional to the product of the two masses. All right? So, what does that mean? The product of the two masses. Let's go back to, I know you like the math, right? Back to the math. It's a math term. What does it mean? When you find the product, what do you do?
You multiply.
You multiply two things, all right? So we have some masses, all right? This little golf ball has a mass, right? You have a mass or whatever. So we have two masses, like we have this golf ball, we have the Earth. It also has a mass. So the gravitational attraction between the golf ball and the Earth, right? One of the things is proportional to the product of the two masses. So if I take the mass of this one and the mass of the Earth, multiply them together, right? Then if I take the golf ball and I make it much bigger, right? Make it much more mass, what's going to happen to that product?
It's gonna get bigger.
It's going to get bigger, right? So what it's saying is the bigger the masses of the two objects are, the more gravity you're going to have. Okay? Then it says it's inversely proportional to the square of the distance. Right? So what that means is if I take the golf ball, your head, right? Your head has some mass, the golf ball has some mass. Right? So there is a gravity, there's an attraction between your head and this golf ball. There's an attraction between your head and her head. And your head and my head, right? Because we all have some mass, so there's a gravitational attraction between us. Right? Now, the amount of as we move the golf ball further and further away, right, from your head, that attraction becomes less and less and less, right? And so it's inversely proportional. In other words, the bigger the distance gets, the less the attraction is. Right? Is what that means. That's pretty simple. All right. Now then, the direction of the force is between the centers of the two masses. All right. And take the center of your head, right, and the center of the golf ball, and so the direction of the force would be in this direction. If I move it over here, the direction would be this way, right? If I moved it up here, the direction would be like this. Now, so Sir Isaac, as I said before, right, one of the things that he was interested in is the apple falls out of the tree. No matter how tall the tree is, the apple's going to fall down and hit the ground. Right? Why does the moon stay up there? Because there's going to be a gravitational attraction between the Earth, it's got one mass, the moon has another mass, and there's a gravitational attraction between the two. Why didn't the moon just fall down? Bang into the Earth? That was the big question. It took him 20 years to figure all of that out. I mean, he thought about it for a long time. But basically what happens is, we talked about me throwing the book a while ago. If I take this ball and I throw it, and I don't throw it very fast, what's it going to do? It's going to go out, and it's going to fall down and hit the ground there. If I throw it real hard,
It hit the wall.
it's going to go further, right, before it hits the ground, right? If I throw it really, really, really hard,
More further.
it's going to go even further. So it's all rocket science. One of the illustrations everybody likes to use is this. We got a little picture of the Earth, and we got a cannon sitting up here on the top of a mountain, or in this case it's on top of a big box, right? And we put a cannonball in it, we pour some gunpowder in there, and we light it off, boom, right? We don't put much gunpowder and make it go very fast. What it does is it falls to the Earth's ground, right? So it's going to fall down and hit the Earth over here somewhere. Right, put a little more gunpowder in it, what's going to happen?
It's gonna go further.
It's going to go a little further, right? If we get it just right, get its speed just right, what's going to happen is the cannonball's going to go all the way around over here, right, and come back here and clunk the guy in the head, right? The fired his cannon, okay? So if I were to take my little golf ball now, and if I were to really, I could throw it fast enough, right? What's going to happen is it's going to be going, the gravitational field is going to be pulling it down towards the center of the Earth all the time, right? But if my golf ball starts out fast enough, it's going to go all the way around. Even though the gravity is constantly pulling it in towards the center, it's going to go around in orbit, right? And that's what happens to the moon. The moon somehow got captured in the Earth's gravitational field, right? But when it did, it was going fast enough, right? So that instead of falling down eventually towards the Earth, it just orbits around it. Same thing, it took us quite a long time after Newton came up with this idea, right, for us to get our little rocket ships designed and built, right, and put our satellites in orbit, right? But they work the same way. What we're doing is we get the satellite up there and we get it going fast enough, right, and we can put it in orbit, right, and make it go around it. We get it going really, really, really fast. It escapes the Earth's gravitational field and heads off out into outer space. If we were going to take and send a rocket to the moon, for instance, or wherever else we're going to send it in the outer space, we got to get going fast enough. And we have a couple of velocities that we have to reach, right? For it to escape, it has to get to going about 25,000 miles an hour. Right? Now, for it to be in orbit around the Earth, right, then it goes a little bit slower than that. And how fast it's going depends upon how high you want to make it, right? If you get it, the faster it goes, a little higher up it gets, right? So one of the, what does it say, 17,000 miles an hour, it's at what altitude? About 150 miles, right?
Yeah.
So we wanted to put a spacecraft up, right, a satellite for our television or whatever, right? We wanted 150 miles up, right? We got to get it going about 17,000 miles an hour for it to be able to do that, for it to stay up there. All right. Questions? No? Okay, let's do another little experiment. Right? You remember what this is, right? It's an
Right.
inclined plane. Who did you have for 6th grade?
Miss Rattel.
Miss Rattel? You did inclined planes. I know you did, right? And so this is an inclined plane. And I've got it propped up on the book there now. I want you to, you're going to be the catcher, Caroline. You're going to catch the ball. Right? So what I'm going to do is I'm going to let the ball go. And if we work it right, maybe it'll roll straight down. Right? What about it? What made it go down the ramp? For our inclined plane. What made it roll?
Gravity pushing
Gravity
it.
pushing it? Okay. What if I take this inclined plane and I go this way? What happened?
It fell straight and faster.
And faster, right? It started out up here at 0, right? But as we let go of it, right, and it started to roll, it started going faster and faster and faster. Right? And what causes that?
The gravity.
Gravity. If I take it and put it like this,
Oh.
ooh, and I put it up here like this, right? And I let it go. It started at 0, it accelerated,
Yeah.
right? And what rate did it accelerate at?
Real fast.
Real fast, okay. 32 feet per second squared. For every second it went down, all right, it's going to get 32 feet per second faster. So that's the acceleration of gravity, so it's like that, it's faster. Right? Now, why, I have another question for you. If I take this book, I go like that, what happens?
It slides.
It slid, and what happened to it?
It stopped.
It stopped. Why?
Gravity.
Well, gravity's pulling the book down on the table, but why did it stop?
Because it's not falling nowhere. It just goes straight.
Okay, what stopped it?
The table.
Friction. Right? If I were to take this up here and I were to somehow maybe go through the air like that, right? It's going to go further, right?
Mm-hmm.
With the same force, it'll actually go further because there's it's passing through the air. There's no friction down here. But if I take this like this and I push it like that, right? There's some friction, so it's going to slow down real quick.
Mm-hmm.
Okay. In order to keep it going, I'm going to have to keep putting some force to it. Now, so if I take this ball though and I roll it, right, it goes further. Why?
Because it's round. So
Because it's round.
it can keep rolling.
It keeps rolling. So what happened to the friction though? There's less friction on this rolling ball. That's why we have our tires are round, right? right? Because there's less friction. If we had flat tires like this, right, on our cars, we'd have a lot of friction. We wouldn't be able to do anything much with them, right? Certainly our gas mileage wouldn't be very good. So this, if I roll it like that, what is my friction is reduced, right? And I have something called rolling friction. Right, this is really sliding. It's sliding across the whole surfaces down there, right? But when I take this ball and roll it, right, there is still some friction, right? Neglecting a little bit of friction because it goes through the air, but there is something called rolling friction. And rolling friction, what it is, you said this was round, right?
Yeah.
Well, it is, until I set it down there like that, right? And no matter what it is, if it was that ball or a marble or whatever, and I set it down there on the table, it's no longer round. You're looking at me like, this guy's gotta be nuts, okay? But it's sitting there on the table, right, and there's a force pulling down on it a little bit, called gravity, right? And then how hard it pulls down on it is dependent upon what the mass is, right? Because we know that the amount of gravitational force we have is dependent upon the mass of the two objects, in this case, the Earth and the ball, and the table's an object too, so it has some mass, so there's gravitational, but we won't get into all that, right? But, so it's pulling down on it just a little bit. And when it pushes down on it, down here on the bottom, a little teeny tiny flat spot, right? So the ball isn't really round anymore. It's got a little flat spot on the bottom, right? So if I take a marble and put it down there like that, it's got a little flat spot on it. And as it rolls, what happens to that little flat spot? It changes, it moves, right? And that's what causes the rolling friction. So to get away from the rolling friction, what you want to do is you want to make this thing as hard as it possibly can be, right? And you want to make this as hard as it possibly can be, so that that little flat spot, the harder it is, the less flat spot you have, and the less rolling friction you have, right? So, I only say that because our next experiment that we're going to do, we're going to have some rolling friction, right? And normally, if we were going to do this and we had some real precise measuring kinds of instruments, what we would use is get a real hard steel ball, and we'd have a real hard steel track that we were going to put it on, right? And do the experiment with those. That way, the little flat spot gets smaller and smaller and smaller, right? And the rolling friction becomes less, right? Which is important because, going back to your automobiles again, the wheels, when they turn, right, they have some little ball bearing things in there, right? And they're made of a real hard steel. And the harder the steel, the less rolling friction they have, and the easier the wheels are to roll, and the better gas mileage you get on your car. All right, so we're going to take this and get rid of this. I'll put my rocket science book back over there. I'll put the ball there for a moment, and we're going to go over here and get this thing. Did you ever do this one?
No.
All right, so what we have is we have 3 ramps. They're not nice and straight like this one. Right, we have a blue ramp, which starts off here, right, and goes down pretty steep, okay? Then it sort of levels off and goes almost flat for the rest of the way. Now that blue ramp is if we were to put our ball up here and start it off to roll, right, it's going to roll along here pretty slow, right, because it's sort of like this, right? But then when it gets here, what's going to happen?
It's gonna go faster.
Pick up speed.
The slope on the ramp is very steep, right? So it's going to go faster when it gets down here, right? So it's going to be accelerated down here. So what's going to happen down here? The acceleration is going to slow down a little bit. The green one is sort of the same way. We have a yellow one in here, right, which is just straight, and then we have this red one, which is basically pretty level across the top. It does drop off a little bit, and a steep slope at the end. Okay, so now what we want to do, we want to do an experiment, and we want to see which one of those ramps the average speed of the ball is faster. Right, you have any idea which one it might be? Which one do you think's the average speed is going to be faster?
The yellow one.
Hmm?
The yellow one.
The yellow one? What do you think?
I think the blue one.
You think the blue one?
Yeah.
All right, well, hey, let's find out. Okay, we have a stopwatch. All right, so what we need to know first of all is, I'll put a piece of paper over here because somebody's going to have to write some things down. We need to know, you want to measure the length of the ramps? Huh? You want to do that?
Sure.
In centimeters, right? I'll let you do it. I'm not going to do all the work. Oh, no, wait a minute. Hold it. You can't pull it up there like that. You got to hold it down.
Yeah.
Right.
It's the other way around.
Okay, let's turn it over because we want to do this pretty accurately, right? This graduation's on here a little bit better, right?
91
91
and a half.
91 and a half, right? Write it down somewhere. Red is 91 and a half. All right, let's do the yellow one.
To 86 and a half.
What is it?
86 and a half.
86 and a half, all right? And the green one.
89.
89.
Mm-hmm.
And the blue.
91.
Are you sure that's right?
Mm-hmm.
Okay, so you've got all your measurements, right?
Mm-hmm.
Written down. Are you sure they're exactly right? Okay. So now then what we need to do is we want to start timing these things. And what we want to do is we want to put the ball up here like this. And we want to let go of it. We want it to roll down here. And we want you to catch it on this end so that we don't lose it. You don't have to chase it all over the place. Like I'm doing now. Right? And we want to time it. Now then, how are we going to do this? Who's gonna time? Who's gonna catch? Who's gonna let the ball go? What are we gonna do?
I'll let the ball go.
What is the best way to? You're gonna let the ball go. What are you gonna do?
I'll time.
You're gonna time it. You think that's a good idea?
Mm-hmm.
You think so? All right. We have a little trick. Right. My lunch money. What I want you to do is I want you to put your fingers right here, right over George Washington. Don't hold on to him, all right, like this. And I'm going to drop the dollar bill, and I want you to catch it. What's the matter? You're not too fast. Just see you do it. Right over, yeah, put it
You
down.
do it.
Don't touch the bill.
You're so slow.
You're terribly slow. I mean, you guys are really,
I'll try again.
really slow. You're really, really. Look, I mean, that's how much easier can you get? You want to try it again?
I'll try it again. Had it.
Now then, what I want you to do, I want you to get it like this in one hand, all right? I'll hold your fingers right there like that. I want you to let go and then you try. All right? So, which is faster? Right, what is happening is, by the time you see me let go of it, right, and your brain says, whoa, fingers close real quick, right, there's a delay, right? So, we're off by a little bit, and you never will be able to catch it. I did have one person actually catch the thing, but I think he cheated. Right? But, so, what we want to do, we want to apply the same principle to what you're doing here, right?
Okay.
Whoever lets go of the ball times it, starts the timer when they let go of it, and stops it when it gets to the bottom. The other person, all they have to do is stand here and catch it, right? So we get a very accurate timing, right? And what we're going to do is we're going to do like three times, right? Or well, let's do one. We should do three, but let's just do one.
You have to time it because you don't want to let me go.
Yes, go ahead.
I'll catch it.
All right, so, oh. What did you get?
2 seconds and 13 milliseconds.
2 what?
seconds and 13 milliseconds.
Okay, we better do 3 then. All right? Let's do 3. So did you write the 2 seconds down? Or whatever you had?
I read it. 1 second.
1 second, all right.
Mm-hmm. 1 second, 74.
Okay.
One second and 27.
All right, so now then we've got the times, right? And you said what? The first one, the red one was what? How many seconds?
2 seconds and 13 milliseconds.
2.13.
13.
All right, and what was the yellow?
1 second.
1.0 and green
74. 74.
1.74 and the blue
1.27.
1.27. Okay, so now then we want to find the speed. All right, so the speed, what are we going to do? You're going to divide what by what? We don't know how many centimeters per second it's going, so what we want to do is we want to divide the centimeters, right, by the second. So what is it for the red? Here's your calculator. You want to divide 91.5
91.5
by 2.13. What do you
That's 42.95. So
get?
it's
40, what?
0.95.
0.95 centimeters per second. All right, what's the yellow one?
$86.5.
86.5, right? And what's the green?
49.42.
49.42. And the blue?
71.65.
71.65. All right, so which one's the fastest?
Red.
Red? Well, the yellow
Wait.
The yellow was going 86.5 centimeters per second, right? That's the bigger number, so
yeah.
that's faster. Which is the next fastest?
The blue.
The blue, right? So we had the yellow was the fastest, then we had the blue, which is the next fastest, and then
The green.
the
And
green,
then the red.
and then the red, all right? So the red one was the slowest, right? And let's see if we can figure out why that is, right? On the red one, which was the slowest, we're coming across here like this, right? And there's what about the slope on the ramp right here, from here to here? It's pretty low, right? It's sort of like having this thing almost flat, right? So what's it going to do? It's going to go very slow down here, right? Until it gets to this spot. And then what happens to the ramp?
It slopes down.
It slopes down, so what's going to happen to the ball?
It picks up
Starts
speed.
It's going to pick up speed. It's going to start accelerating it, right? So the final speed that it's going to have is whatever little bit of acceleration it gets here, right, versus this high acceleration it gets here, which is late in the game, right? And that's going to determine speed. Where on this one, on the yellow one, which was the fastest one, it's straight slope all the way. There's no real level spots, so it's going to go
Straight down
straight down, and it's going to be accelerated
the whole way.
a little bit faster, right? So it's going to be the highest one. Where this green one is sort of the same shape as the red one, right? It starts off sort of flat, and then it's got a little ramp that goes down, but it's not as steep as this one, so it's not going to accelerate as much, right? And then it flattens out off on the bottom. Right? The blue one, which was what? Was the next fastest one?
Yeah.
Yeah.
Right. So it starts off here, right? And very little acceleration here, but when it gets to the steep part, it's going to really come down, right? And then it's still accelerating a little bit, right? But it's picked up enough speed here early in the game, so it's really going fast across here. So it was the next fastest, right? We were off a little bit in our calculations because what we should have done is we should have tried 3 times. We got an average time for it to come down, right? But we only did it once. So, but anytime that you do an experiment like this, right, because you're off a little bit when you click the button, right? Sometimes you click a little bit early, sometimes you click a little bit late. So we should have done it like 3 times. But we're still in the ballpark, all right? We come out with the right relative answers, all right? They're not precise, but they're very close. So, why do you think we're doing Newton today? And gravity and all that sort of thing? Because it's getting close to Christmas. All right? And good old Sir Isaac Newton was born on Christmas Day.
Cool.
You didn't know that, right? Cool. But, hold it. Let's back up a little bit. What's my chart say he was born?
January 4th.
January 4th. When's Christmas?
December 25th.
It's December 25th. Well, am I all messed up or what? If he was born on January 24th, how can he be born on Christmas Day? What'd you do, catch me in a lie or something, huh? I got all messed up? The reason is because back in 1643, right, they were using a different calendar, right, and they weren't using the same calendar we have today. These dates here are based on the calendar that we're using today, right, which makes it January 4th. But back when good old Sir Isaac was born, right, they had a different calendar, and he was actually born on Christmas Day, according to their calendar, right? And over the period of years, we've changed calendars several times, right? Because they weren't all very accurate, right? So we had to keep changing things. So even if you do, I know you're getting ready to do what's the unit you're going to do is people and environments and so forth, and basically hereditary kinds of things. And if you go back and start doing your genealogy, right, find out where all your ancestors came from, you go back just a few years, and you don't have to go back very far, the dates get messed up, right, because they used a different calendar, right? So you got to be, when you get back several hundred years, you got to make sure you know what calendar they were using, so you know what day the people were born and died and so forth, right? So that's it. So, and one of the things that some of the schools do is to celebrate Sir Isaac Newton's birthday, because it's, he discovered a lot of things for us, right? Is they have some races, right? What they do is they go out in the hallway with a ramp. Everybody brings a can of food, some kind of food, and they let it go down to the ramp. It's always fixed, all right, so they nobody cheats, make one steep, one sort of flat, right? And they the cans roll down here, right? And then measure how far they go down the hallway, right? And the person whose can goes the furthest is the winner. And then they take all the cans, right? And they donate them to one of the food banks for Christmas. So that's one of the things that some of the schools do. So, Sir Isaac Newton, right? We know that he didn't get hit on the head by an apple, or at least we don't think he did, right, and just all of a sudden discover gravity. He may have seen some apples fall out of the tree, he may have seen some things fall down, right? And his really first important document that he wrote, right, was on the gravitational forces between all the elements in planets and moons and so forth in our solar system, right, and how they react. Why does, if an apple falls out of the tree, hits the ground, why doesn't a moon fall down and hit the ground too, right? And up until that point in time, nobody had really, come up with the idea. So it was a brand new idea. All right, so that's it for today. And what we're going to do now is we're going to do a little rocket science. See, we're doing rocket science today, right? Rocket propulsion. And all these old guys in here. But can you imagine? This is a launch site. You know, like they have down at NASA now, where they launch the rockets. Okay, these guys are out here and they're in a hole in the ground.